Hello, my name is Mark Kittisopikul, and I'm a software engineer at Center Computing at the JuliaCon Research Campus of the Harvard Hughes Medical Institute. Today I'm going to talk to you about ArrayAllocators, which is a package that extends the abilities to allocate memory for arrays in Julia. It in particular provides new mechanisms to do so, and NUMA allocators.jl, which builds upon ArrayAllocators for high performance computing. This is a talk given in part for JuliaCon 2022. So one motivation here that I had to create this package is that when benchmarking NumPy versus Julia, I found that NumPy zeros can seem faster than base set zeros. So we take a look. It takes tens of microseconds to allocate an array of 64-bit floats in NumPy. Doing something similar in Julia takes on the order of a second. So this seems to be much faster in NumPy than in Julia. Let's investigate why and how we can make this easily accessible to the Julia user. So let's just review array allocation in Julia. This talk is meant for a general audience or people who may be new to Julia. So basically, the simple syntax, we can just give the size, and this assumes that this is going to give us a double precision floating point number. This is going to also initialize the value to 0. We could specify a different type, in this case an int, which is an int64, or we can use 1 to initialize to a value of 1, or we can use trues, which will allocate a bunch of booleans. This is a simple syntax that I think is more reminiscent of code from MATLAB or perhaps NumPy. But a preferred syntax is to use this parameterized type constructor. And so here we have some new elements. We can curly braces. There's also this new element here in def. And using this preferred syntax, which I'll go into the next slide, we can then fill this array to initialize it. Another mechanism I want to mention here, I don't have time to go into, is based on safe wrap, which underlies the implementation of this package. So let's talk about this preferred Julia syntax and why we prefer it. In particular, this allows us to specify the array type. And that could be an array or an offset array or other kinds of arrays that may exist in base Julia. And this is something that we couldn't do using the functional syntax such as zeros. Furthermore, we can specify the element type, which would be like int or float64, as we talked about before. We can also give the size as we gave before, either as a tuple or just a list of arguments. But also there's this initializer thing, which currently there's only, I think, 3 valid values in base Julia, undef, nothing, or missing. And this package, ArrayAllocators, provides a mechanism to extend the syntax so we can use different kinds of initializers. Now, I would call initializers, I put this in quote, because really not all these mechanisms that we use here are actually initialized in memory. Some of them only allocate the memory, hence the name ArrayAllocators.jl. So malloc, it just uses a standard C memory allocator, libc.malloc. And that just returns a pointer and we wrap it and then provide an easy syntax to do so. That's pretty similar to undef initialization. Calloc is a new mechanism, however, because this call in standard C acts like zeros. It initializes all the bytes to 0. But it might have some advantages that I'll bring up in just a second. A third mechanism, which I'll also discuss in a few slides, is memory alignment. So calloc is a way to allocate and initialize memory to zeros. And as you can see here, if we use the calloc allocator initializer, it's actually now very fast, as opposed to being on the order of a second when doing using zeros. It's actually pretty close to undef initialization in time, sometimes even faster. Yet, like zeros, it will initialize all the memory to 0, whereas undef initialization does not guarantee that. This will sometimes be true, but it's not guaranteed for every single time. I also provide a functional syntax to this, so you can use ArrayAllocators at zeros, and if you import this right away before you use zeros, you can actually now refer to that just as zeros. So in this case, the first and second instance here are both using ArrayAllocators. You can see this is now fast. This is much faster than using base set zeros, at least for initial allocation. The details of this are difficult to discuss in the time limits here. We can see this post on Discourse, where Valentina and I kind of discussed the merits of doing this or not. Essentially, what happens with calloc is the operating system can take advantage of its knowledge of the memory. It knows it has a zero memory before it gives it to Julia, and so given that state, it knows what pages of memory it's already zeroed out and can just give that when you request it. As opposed to base set zeros, which uses memset to eagerly clear the memory with zeros. This can confound your benchmarking, so you should really carefully benchmark everything you're doing when using this package. In particular, allocation time may actually occur when you're trying to write to memory as opposed to this initial call, so be careful. Memory alignment. So mem_align is a constructor that allows you to specify where your memory is aligned at what boundaries. And this is an optimization that can be particularly important when using advanced processor instructions such as SIMD or AVX512 in particular. So we try to allocate an array using undef in Julia. We see that the pointer is aligned to 16 bytes here, whereas there's a much more zeros here when we especially ask for alignment to 2 to 16. So this is optimization you can use for advanced operations. This takes advantage of an underlying positive mem line and is analog in Windows. This should be relatively cross-platform. Extension of ArrayAllocators is NUMA allocators.jl. This refers to non-uniform memory access. And this is particularly important when you're using multiple processors in high-performance workstations and compute nodes. So NUMA allocators basically allows you to allocate memory on specific NUMA nodes. So the initializer can be constructed by calling the function NUMA and just passing the node number that you want. This is zero-based. And this is available for Linux and Windows. And if you know about NUMA mechanisms and other operating systems, please reach out. How to use this? Well, here we allocate two arrays, A and B on NUMA node 0, and two arrays on NUMA node 1. We see that actually that when we're trying to copy memory between arrays, and actually I've omitted filling these here for this slide, but we see that copying between local memory allocations is actually relatively slow, whereas copying from the local memory to remote memory is actually the fastest. And so NUMA allocators gives you perhaps access to new optimizations that you may be take advantage of in your application. Again, please benchmark your application thoroughly. So in summary, ArrayAllocators.jl is a basic framework that adds new ArrayAllocators to Julia through the standard syntax. It in particular provides new initializers or allocators, as I prefer to call it. One particular initializer that is interesting is calloc. This allows us to lazily initialize an array of zeros, more similar to the way NumPy implements their zeros function. Additionally, I've discussed NUMA allocators, which extends array allocators for high-performance computing applications. You have multiple processors. There's some acknowledgements. I just want to acknowledge Julia, HHMI, Lavin Philip Keller, especially Raka Chetri and Mekwan Wong, with whom I work and where I discovered many of these techniques, and also Center Computing Group and Stefan Privish, the Director of Center Computing. We happen to be hiring, so please check out these links. Here's a link to the package and documentation. And there's a few topics I have not discussed. For example, how do I handle integer overflow for memory and type safety? And also, how might I use this to extend for other allocator schemes such as JEmalloc or bmalloc? And I also kind of have some ideas for how we might implement custom memory allocators in Julia. And that's it. Thank you very much.